Hello, my name is David Hanch, and I will be explaining how to calculate the stability of the vessel in this section. The stability of the vessel is measured in terms of GM, which is the distance from the center of gravity to the metacenter, and that can be shown in this plot here, where we've plotted out a few of the points that we're going to discuss. The metacenter is this location up here, and basically that's the location that the vessel moves about for small angles of roll, and actually in the longitudinal direction it trims about this location as well. So the way we calculate that is based on the formula GM equals KM minus KG, and we'll break down how to calculate each of the pieces of this. Some of the pieces of some of these calculations you've seen how to calculate in other sections, so we'll reference those, but we won't actually calculate them again. So the first part we need to calculate is the distance from the keel to the metacenter. And the equation for that is Km equals Kb plus Bm. Now, Kb is the same thing as VCB, which you already calculated. So we won't calculate that again. But we do need to calculate Bm. Now, Bm equals the moment of inertia of the water plane divided by the displaced volume. And if we were calculating GMT, which we are in this example, the moment of inertia about the water plane would be the transverse moment of inertia of the water plane. Now, using the box barge example that we've used before, looking down on a plan view, the length of the barge is 6 feet and the beam is 2 feet. And for a rectangle, the equation for the transverse moment of inertia of the water plane is length times beam cubed over 12. And if we plug in 2 and 6, 2 being the beam and 6 being the length, into this equation and divide by 12, we will result in 4 feet to the fourth as the transverse moment of inertia. Now this is about a point on the center line of the vessel, and that's important because that's where it needs to be. And I'm going to show you another method which will calculate it about a point on one edge, and then we'll have to move from the edge into the center line, and I'll show you how to make that correction. So the alternate method of calculating, and the method that you'll probably have to use because you probably won't have a rectangular water plane area, is using Simpson's rule. It's a different twist than the Simpson's rule you've seen before. And that equation is I sub t equals 1/3 times h over 3 times the summation of the beam cubed times the Simpson's multiplier. And in this case, all of our beams are going to be 2 feet. So if we plug that in and work out the whole form, we will get 1/3. And if we stop for a second and calculate h, we're going to divide this into 5 pieces. So that will mean that there's 4 intervals. There'll be 4 intervals. So the h will be 6/4. plug in 6 over 4 for h here, and a 3 here. And then we'll multiply by the quantity of 2 cubed plus 4 times 2 cubed plus 2 times 2 cubed plus 4 times 2 cubed plus 2 cubed. And if we combine this, we get an answer of 96 inside the... And the units on this are going to be feet to the fourth. And if we multiply that then by the outside, which is 1/6, we'll get a total IT of 16. You'll notice that this 16 does not agree with the 4 that we calculated before. And that's because, as I said before, this formulation calculates the transverse moment of inertia about the one edge of the shape rather than about the center of the shape. But we need the center of the shape for our equation. So to correct for that, we use the parallel axis theorem, which says that the new moment of inertia equals the old moment of inertia plus the area times the distance squared if you're moving from the centroid of the area to a point off the centroid of the area. But in our case, we're moving from a point off of the centroid in the area to the centroid of the area. So this plus sign goes away, and we use a minus sign instead. So the distance that we're moving is 1 foot, half of the beam. So our subtracted area is just the area, or 12 feet. 12 feet to the fourth. So our resultant IT is also 4 feet to the fourth, which agrees with the IT we previously calculated. So based on using the transverse moment of inertia calculation shown here, dividing by the displaced volume, which we've already calculated in other segments, you can arrive at BM, or the distance from the center of buoyancy to the metacenter. We already know, as noted before, we already know the distance from the keel to the center of buoyancy. That's the vertical center of buoyancy that was calculated in other segments. So we can calculate Km from those two values. And we already know Kg, or the vertical center of gravity, from other segments. So from that, we can calculate GM, which is the measure of stability. Now, GM should be positive. And I believe there are guidelines for GM in the guidelines. The larger GM is, the more stable the vessel is.